Okay. So let's see, number 2. So we've got this super cool hot rod, right? And the hot rod has little wheels in the front and big wheels in the back. All right, there we go. All right. It gives us a bunch of information. So let's see, the rear wheels. So here's what we know about the rear wheels. We know that they have a radius of 0.70 meters, and that the front wheels, let me do this, let me write this by the rear wheels. That probably makes a little more sense. If you are spatially, I don't know what the word I want there is. All right, and then let's see, the front wheels are smaller. They have a radius of 0.2 meters. Okay, and so the car accelerates. All right, so the deal with this is as the car moves, obviously both wheels are going to move, and they're both going to spin. All right, so at the crux of this problem is that both wheels have the same linear values, right? Because they're attached to the same car. All right, so all this information about the velocity of the car applies to both wheels. All right, so we know that the car has an initial velocity of 20 meters a second, and then it's going to slow down at 4 meters per second squared. Don't forget that negative sign. All right, these numbers also apply to the front wheels. Okay. Now the question wants to know what's the frequency of the front tires. So it's sort of the final frequency. What's the final frequency of the front tires at the instant at which the rear tires have rotated 6 times? So our delta theta is 6 rotations, which times 2 pi, that's the same as 12 pi radians. Okay? So, again, crux is same linear values. So if I want to find this final frequency, I need to find the corresponding final angular velocity or the corresponding linear velocity, right? But this linear velocity here for these front tires is going to be the same as the rear tires. So let's see if we can find the final velocity of the rear tires. So we're looking for a linear value. Most of our given values are linear. So the only thing that's not linear is this thing, right? So let's find the corresponding linear displacement for the rear wheels. So our displacement is, oh, well, I can just use a jumper. It's delta theta times r, right? So 12 pi radians times the radius is 0.7 meters. So if you multiply that, it gives you a number which is 26.39 meters. All right, so now I believe that I ought to be able to use my VI, my A, and my delta X to find my VF, right? Because I can use this guy, 2A delta X equals VF squared minus VI squared to solve for VF. Okay, so if you plug in those 3 yellow highlighted numbers, you discover that the VF for the rear wheels is 13.74 meters a second. Okay? But that means that the VF for the front wheels is also 13.74 meters a second. And so now we can find that frequency. So there's a couple of ways you can do it. I guess I probably would just do it in one step and use this guy, V equals 2 pi RF, and solve for frequency. Or you could use a jumper, and once you've got that, convert it over to radians, right? So, all right, so either of those 2 things will work. This latter one probably is maybe more where your head was at, so I guess let's do it that way. So let's see, so we know our velocity is 13.74 meters a second. We know the radius on those back tires is 0.2 meters, so divide that. And it gives you 68.7 radians per second, and now you just use dimensional analysis and convert. So let's see, 2 pi radians is 1 rotation, so divide that out and you get whatever I said the answer was, 10.9 rotations per second, which is 10.9 hertz, right? Because radians cancel and you get rotations per second. All right, so there you go. That's how you do number 2.